problems from day 2, and then I'll introduce day 3. So day 2, I think probably people would want to know about these last few problems. They're all limit as x goes to infinity problems. This one here, number 10, just like always when you're evaluating limits as x goes to infinity, you're supposed to be considering the fastest growing term in the numerator and the fastest growing term in the denominator, which would be the quadratic terms. Now, there is a square root over the entire fraction. That doesn't really matter. It just means that you're really just working with the square root of the ratio of the lead terms. So you're going to be looking at the limit as x goes to infinity of square root of, and if you just drop the slower growing terms, then you're left with this, which of course simplifies to, after cancellation, after getting rid of the x's, simplifies to just 9 over 16 underneath the square root, and so the value of this limit is just square root of 9 over 16, which is 3 over 4. So it works the way that you would expect. These other two problems, 11 and 12, are trying to get you to realize that when you are evaluating limits as x goes to infinity, you're trying to find the fastest growing term. You can find the fastest growing term in these two expressions in the numerator and the denominator without multiplying out every single term. So in this numerator here, what would be the highest degree term? What would be the fastest growing term? Well, it's going to come from multiplying the 4x with the 2x, and well, you've got two copies of this 3x minus 4 factor. So your lead term, the fastest growing term in the numerator, would be 4x times 2x times 3x quantity squared. And so your lead term would sort of be 4x times 2x times 3x squared. And likewise, in the denominator, the lead term would be the product of the lead terms of each of these factors, which would be x times 3x times another 3x times 5x. And that would give you, let's see, the numerator would be 8 times 9, so 72 x to the 4th, over, and the denominator would be 45 x to the 4th. The x to the 4ths cancel, you get 72 over 45, so that's the value of the limit, unless I made some kind of arithmetic mistake or something. And the next one, number 12, very similar. You're just supposed to say, oh, well, I know what the lead term of the numerator would be. It would be obtained by just multiplying the 2x against itself over and over again, right? That's how you would manufacture the highest degree term from this product, is by taking 2x from each of them and multiplying repeatedly. So the fastest growing term would be 2x quantity to the power of 10, so that would be like 2 to the 10th times x to the 10th. And then likewise, the bottom would be 4 to the 5th, x to the 5th. Now, what you'll notice is that the x's don't completely cancel, right? There are more x's on top than there are on bottom. So after cancellation, you're left with this. And as x goes to infinity, the value of this fraction is not converging to any particular number. It's just getting bigger and bigger, right? This is kind of what an earlier problem, number 9, was getting at, right? If you're looking at the limit as x goes to infinity of a rational function, that is to say, a function where the numerator and denominator are both polynomials, then you can sort of glance at the degrees of the polynomials and draw some fast conclusions. Like, if the degree of the numerator is bigger, so if the degree of this guy is bigger than the degree of that guy, then basically overall the numerator grows faster than the denominator, and the overall value of the fraction is getting bigger and bigger, and so therefore the limit is going to some kind of infinity. On the other hand, if the denominator degree is bigger, then the denominator is growing more quickly than the numerator, and so overall the value of the fraction is getting smaller and smaller, and the value of the fraction is approaching 0. And then finally, if the degrees are equal, in that case, you wind up with the limit being the ratio of the lead coefficients, so a sub n over b sub n. All right. Well, anyway, let's talk about day three. So day three, there's not necessarily a lot of new content in day three. We're really just introducing some additional interesting functions that serve as good examples for thinking about limits. And the first one that if you sort of glance ahead, you'll see we introduce the greatest integer function, or this is sometimes called the floor function. You'll see we introduce some piecewise defined functions, and we also start introducing functions involving absolute value. And those are all very good examples of limit problems. You'll also see we start introducing square roots in some of our functions. And so we're just going to spend some time thinking about how to evaluate limits involving each of those kinds of functions. So let's start with the first example. Example number one, this guy right here is the greatest integer function. Greatest integer function, it means, this guy is the greatest integer which is less than or equal to x. That's kind of a strange way of describing it. I think it's much easier to understand that all this function does is it rounds down. It just rounds down to the nearest integer. So if f of x is this function right here, the greatest integer function, or sometimes people call it, as I say, sometimes people call it the floor function, then what is f of 2.3? Well, the function just rounds that number down to the nearest integer. So 2. F of 2.3 is 2. What is f of 0.5? Well, you just round down. So that would be 0. What is f of 1? Well, 1 is already an integer, so it's just 1. What is f of negative 0.5? Well, you round down, right? You always round down with this function, so that would be negative 1. What is f of negative 1.3? Once again, you're going to round down, so that would be negative 2. And just, take a moment to recognize that what this function does, it's not rounding to the nearest integer, right? It's not rounding to the nearest integer. It's always rounding down, right? So just bear that in mind. Sketch a graph of f of x. I'll show you the graph in a second. Probably you should pause the video and just try to think for a second on your own what the graph of this function looks like. I'll give you a hint. It's kind of like broken up into pieces. It's kind of like a stepwise looking function. So maybe just pause, try to think of what the graph looks like approximately on your own. Here's the answer. In Desmos, you can graph the round down function by just typing floor of x. Here it is. So you can see that, if you are, let me sort of adjust this, this window here. There we go. So you can sort of see that if you're below 1, you get rounded down to 0. If you're between 1 and 2, then you get rounded down to 1, and so on. So that's what this guy looks like. And then they ask you to evaluate each of the following limits. Of course, if you've got a fabulous graph right in front of you, then evaluating these limits is not so hard. So for example, what is the limit as x approaches 1 from the left of this function? Well, if I look, here's x equals 1, and if I ask what happens as I approach 1 from the left, well, my function is just constantly equal to 1 throughout that process. And so, whoa, what am I saying? No, from the left. I made the mistake that I warned people not to make. From the left means from over here, of course, right? As x is approaching 1 from the left, we're approaching from over here. Sorry, I kind of have a cold. I'm going to blame that for that mistake. So we're approaching 1 from the left, we're over here, and as you can see, the function is just constantly equal to 0 throughout that process, and so the limit is equal to 0. If you approach 1 from the right, then approaching 1 from the right, you're over here, the function is constantly equal to 1, so that limit would be equal to 1. Now, can you do this without looking at the graph? Oh, and maybe we'll talk about this. So what is this guy? Well, that guy doesn't exist because the left and right hand limits don't agree, right? The left and right hand limits are two different numbers, so the two-sided limit does not exist. Okay, the end. Now, what's going on here? Limit as x approaches 2. Well, that's a two-sided limit, right? That's a two-sided limit. The same thing that happened at 1 is going to be happening at 2. if you approach 2 from the left, the entire time that you're approaching 2, your x values are like 1.8, 1.9, 1.99. All of those values are getting rounded down to 1. So you approach from the left, you're going to be getting 1. On the other hand, if you approach from the right, you're going to be getting 2, and because those two limits don't agree, because the left and right hand limits don't agree, they aren't equal, this two-sided limit does not exist. But how about this guy? Two-sided limit at x equals 2.4. Well, in this case, it doesn't matter from which direction you approach. If you approach 2.4 from the left or the right, the entire time you are getting rounded down to the same number, 2. So this guy does exist. It's just equal to 2. And then finally, what is this guy? Well, that's just infinity, right? Because as x keeps increasing, the value of this function just keeps getting bigger and bigger. Okay, so that's the round down function. Now we'll consider this piecewise function. Sketch a graph of this guy. Do I really want to do that? I guess I can. I mean, I do have Desmos open right here, so it would only take 2 seconds, right? So I guess I'll just go ahead and do that. So I'm going to write f of x equals x squared minus 5, but I only want that to be plotted for x less than or equal to 3. I'll give a different name to the second piece, square root of x plus 13 for x greater than 3. So what does this guy look like? Well, if I zoom out, you can see that the two pieces, one of them is a quadratic, of course, and the other one is some kind of a root function, and it changes at 3, and so there you have it. So that's what that function looks like. Let's evaluate each of the following limits. What is the limit as x approaches 3 from the right? Well, if you have the graph in front of you, then it's very clear that as you approach 3 from the right, the value of the function is approaching 4. But the way that you would do that algebraically without consulting the graph is you would say, oh, well, as x approaches 3 from the right, that means that x is greater than 3, right? If x is approaching 3 from the right, that means that x is bigger than 3, which means that you'll be considering this region, right? That will be governed by this function. And so to evaluate this limit, you would plug 3 into this function, which would give you root 16, which is indeed 4. So that's how you see it algebraically. Likewise, this guy here, limit as x approaches 3 from the left, if you have the graph in front of you, it's perfectly clear that the left-hand limit is also 4. But if you don't have the graph, you can just say to yourself, well, as x approaches 3 from the left, that means that x is less than 3, so 2.8, 2.9, and throughout that region, we're in this region here, that region is governed by this function, and so to evaluate this limit, I would plug 3 into this function, which would be 3 squared minus 5, so 9 minus 5, which is 4. And then finally, what is the two-sided limit? Well, since both the left and the right-hand limits were the same number because they were both 4, this two-sided limit does indeed exist, and it's just equal to 4. So that's what that guy is. Okay, now for number 3, write f of x equals absolute value of x as a piecewise function. You maybe haven't thought about the absolute value function as a piecewise function before, but if you think about it, it's very natural to describe it that way because, a piecewise function is just a function which has different rules depending upon the value of x that you're plugging into the function, and that perfectly describes what the absolute value function does, right? The absolute value function has two different rules, one for when the input is a negative number, and another for when the input is 0 or positive. And so that insight is kind of a clue about how you can write the absolute value function as a piecewise function. So the absolute value of x can be written as a piecewise defined function. Curly brace, there we go. So, of course, there's one rule for when x is less than 0 and a different rule for when x is greater than or equal to 0. Now, obviously, let's start with the second rule because it's kind of easier. When x is greater than or equal to 0, the absolute value of x is just x itself, right? The absolute value function does nothing in that case. Now, what does the absolute value function do when x is negative? Well, of course, people usually say, well, what it does is it makes the number positive. That's fine, but how does it do that? Well, one way of describing it is the absolute value function makes the number positive by multiplying it by -1. So the absolute value of x when x is a negative number is actually opposite of x. Okay, and sometimes people get confused about that because they say, oh, what is this negative x stuff here? Isn't the absolute value of x supposed to be positive? Well, yeah, it is, because if x is a negative number to begin with, then the opposite of x will be a positive number, right? So if x is already negative to start out with, then the opposite of x will in fact be a positive number. So that's how you describe it as a piecewise function. And then it says, write this guy as a piecewise function. You could do that. I don't really know if that's the best use of your time. You could say absolute value of x over x is equal to, well, it's going to be the same formula, except you're going to divide, each of these guys by x, right? If you divide this by x, you get -1. You divide this by x, you get +1. There is one slight issue, though, here. This function's not actually defined for x equal to 0, and so I should really change this greater than or equal sign to a strictly greater than sign, right? So this guy here, yeah, it's -1 for negative values, and it's +1 for positive values, and then it's very clear, why the two-sided limit does not exist. They're sort of saying, explain why using proper limit notation. I'm going to do that. I actually don't think it's a great way of. I actually don't think that you need to do this. Like, I don't think that you need to write this as a piecewise defined function. Here's what I would say. I would say, if you want to evaluate this guy, right, the two-sided limit as x approaches 0 of this function, you plug in 0, right? You plug in 0, and you get 0 over 0, and that means, right? I mean, this is what I told you guys, right? I sort of said, if you're trying to evaluate a limit algebraically, then your first move should be to plug in. And if you plug in, you get 0 over 0, one of those indeterminate forms. And normally what that means is you need to simplify. Trouble is, there's no way to simplify this expression. Like, maybe you'd like to cancel the x's or something, but you can't, because the absolute value bars are preventing this x here from interacting with the other x. The absolute value bars are like a set of brick walls. And so, in order to simplify this function, you have to analyze what the absolute value bars are actually doing, okay? And what those absolute value bars are doing depends upon whether x is approaching 0 from the left or the right, because it depends upon whether x is a positive or a negative number. So if I look at the limit as x approaches 0 from the left of this function, well, if x is approaching 0 from the left, that means that x is a negative number, which means that the absolute value of x is actually the opposite of x. And so what I've done here is I've analyzed the absolute value function based upon the direction from which x is approaching 0, and I've said, oh, absolute value of x has to be opposite of x in this case. And now that I've analyzed the absolute value function, I can cancel these x's, right? I can actually simplify this, so I get limit as x approaches 0 from the left of just -1, which is, of course, -1. On the other hand, if I take the limit as x approaches 0 from the right of this function, well, in this case, because x is approaching 0 from the right, that means that x is a positive number, which means that the absolute value of x is just x, and so this expression simplifies to simply 1. And so the right-hand limit is just 1. These two, so since the left and right-hand limits don't agree, the two-sided limit does not exist, is what we could say, if we wanted to be very formal about it. Okay, so that's example 4. Find this guy. They say, think of writing this as a piecewise function. I don't know if it's the best strategy to write it as a piecewise function. I think you're better off just like analyzing what the absolute value function is doing depending upon whether x is a positive or a negative number. So let me just do that. So this is example 5a. So limit as x approaches 0 from the left of, I'll put this in parentheses, 1 over x minus 1 over absolute value of x. Well, since x is approaching 0 from the left, that means that the input to the absolute value function is a negative number, which means that the absolute value of x is going to be the opposite of x, right? And so with that in mind, we can simplify. That's 1 over x minus negative 1 over x, so it's just 2 over x. And that is, if you plug 0 into that, you get a non-zero number over 0, which indicates that you have some kind of a vertical asymptote. So yeah, so this is some kind of infinity. Is it positive or negative infinity? Well, if you plug in a number close to 0 on the left, like negative 0.1, you get a negative value, which means that this is negative infinity. Okay. On the other hand, the limit as x approaches 0 from the right of that same function, in that case, the analysis is the same, except x is now a positive number, which means that the absolute value of x is just x, and then this function simplifies to just the limit as x approaches 0 of the constant function 0, which is just 0. Okay, so the right-hand limit is just 0. Before I move on, I want to add an additional example here that the packet doesn't make super clear. Let me show you. Suppose that I wanted to evaluate the following limit. Limit as x approaches 2 from the left of the absolute value of x minus 2 over x minus 2. If you plug 2 into this thing, you get 0 over 0, which means you need to simplify. And in order to simplify, I have to analyze the absolute value expression. Like, what is the absolute value function doing? Now, sometimes what people will say, mistakenly, sometimes people have a misunderstanding about these problems, and they'll say, oh, well, positive 2, that's a positive number, which means that the absolute value function applied to x minus 2 is just x minus 2. That's wrong, okay? What matters is whether the input to the absolute value function is positive or negative. Okay, the entire input. The input to the absolute value function here, the number that's being plugged into the absolute value function, is not x. It's x minus 2. And so the relevant question is not whether x is positive or negative. It's whether this entire expression, x minus 2, is positive or negative. Since x is approaching 2 from the left, that means x is like 1.9, 1.99. And so this expression is in fact negative, which means that absolute value of x minus 2 in this case is in fact opposite of x minus 2. And so that expression simplifies to just -1, and so the limit is -1. So don't make that mistake. Okay, now we come to number 6. The remaining ones are going to be pretty fast. So number 6, if you see your square root floating around in a limit problem, there's a very good chance that what you're supposed to do is multiply top and bottom by the conjugate. Now, strictly speaking, I should plug in the 16. We can do this in our heads, though, right? If I plug in 16, I can tell that I get 0 over 0. So I'm supposed to simplify. How do I simplify? You need to multiply top and bottom. So limit as x approaches 16. You need to multiply top and bottom by what's called the conjugate of the square root expression. So the square root expression in this case is root x minus 4. So what I'm going to do is I'm going to multiply top and bottom by the conjugate of root x minus 4, which is root x plus 4. You've seen similar things, when simplifying quotients of complex numbers, like when you're rationalizing certain complicated denominators. This is a common sort of algebraic technique. Now, Now, of course, we're allowed to do that because we're multiplying top and bottom of the fraction by the same thing, so that's allowed. Now, why would you do that? Well, if you multiply out the root expression times its conjugate, something nice happens, because this guy here is actually the product of a sum and a difference. It's like a plus b times a minus b. And so it will multiply out as a squared minus b squared. A squared is just x, b squared is just 16. Okay. So, I mean, yeah, you can multiply this out manually, like root x times root x, and then root x times 4, and then negative 4 times root x, but you'll get x minus 16, I promise. Now, what we should notice now is that, oh, the x minus 16s cancel, and so that gives you that just gives you 1 over square root of x plus 4, and if you plug 16 into that, you will get an actual value, right? I think you get 1 over 8, so that's the limit. So last thing, so when you see a square root floating around in a fraction like this, there's a very good chance that you are supposed to multiply top and bottom by the conjugate of the root expression. Now, a couple of things about this. Number one, you multiply by the conjugate of the root expression. Sometimes people will look at this first example and they'll be like, oh, Mr. Knott multiplied top and bottom by the conjugate of the numerator, so I always multiply top and bottom by the conjugate of the numerator. No, you multiply top and bottom by the conjugate of the root expression, wherever the root expression appears. If the root expression appears in the bottom, you multiply top and bottom by that, right? So sometimes it's a numerator, but it's always the root expression, right? You're not going to multiply top and bottom by x plus 16. That's not what you would do. So that's the first comment. The other comment is, do you notice that I only actually multiplied out this part of the fraction, like the numerator? I did not FOIL out the denominator, and it's good that I didn't because, since I left the denominator in factored form, I was easily able to tell that these x minus 16s canceled, right? Whereas if I'd multiplied everything out, it probably wouldn't be so clear that there would be cancellation. And so the other comment about this problem type is you only want to multiply out the root expression multiplied by its conjugate, okay? The other part of the fraction, which is just some other expression times the conjugate of the root expression, leave that in factored form, okay? You want to leave that in factored form. Okay, then we get to number 7. 7's kind of a funny one, maybe. I mean, if you plug 5 into this, you get 0 over 0, so, definitely we need to do something with it. So what do we do? Well, there's not really a notion of conjugate here that you could apply, I don't think. But you could try multiplying top and bottom by just the original square root expression, and I think something nice will happen if you do that. So, if you just multiply the top by that root expression and the bottom by that root expression. So, if I do that, and then just I'll leave the denominator alone, but I am going to multiply out the numerator. If you multiply out the numerator, the roots just go away, right? The roots go away, and you get 25 minus x squared. And then on the bottom, you have all of this stuff. At first, that doesn't look very promising. The expression looks a lot worse. But you can factor the numerator, right, to give you, that's the difference of 2 squares, 5 minus x times 5 plus x. And then you can do some cancellation. Watch out, because the 5 minus x is not the same thing as x minus 5, right? You can cancel these guys, but I mean, if you want, you can rewrite this as x minus 5, but then you get a minus sign here, right? So these guys cancel, but you're going to have a minus sign left over in the numerator. So that's going to be limit as x approaches 5 from the left of negative quantity 5 plus x over square root of 25 minus x squared. And if I plug 5 into that, then I get a non-zero number over 0, which means some kind of infinity. It's kind of a bummer. Is it positive or negative infinity? Well, if I imagine plugging in like 4.9, the numerator is definitely negative, and the denominator is positive. So I think it's negative infinity. I'm going to do that again in a totally different way. I think a less stupid way. I think that's the way that they wanted you to do it. Here's a totally different way of doing it, all right, that I think I like more. Instead of multiplying top and bottom by this stuff, like, you can just do this. Like, factor the 25 minus x squared, so 5 minus x times 5 plus x. And then, like, distribute the root. So, like this. You know, and then roots distribute over products like that. Actually, I don't like this so much. Well, no, but here's what I can do. I kind of want to make this guy cancel with the denominator somehow, but I want them to be the same. So let me rewrite this as opposite of 5 minus x like that. And then if you think about this guy and this guy, they do kind of cancel. It's just that there is, like, you know, this is 5 minus x to the 1/2, to the power of 1/2. And this is 5 minus x to the 1. So you can do some cancellation. It's just you have some stuff left over in the denominator, right? You have opposite of 5 minus x to the 1/2 left over in the denominator. Yeah, and if you plug 5 into that, then you get non-zero number over 0, and, you know, the same analysis will give you negative infinity. Is that a better way of doing it? Yeah, I don't really know if it's a better way of doing it, but it's a different way of doing it. Okay, and then finally, last but not least, number 8. If you plug in 3, I'm sure that you get some kind of nonsense. You get 7 over 0 minus 1 over 0. Now, what does that mean? That's like infinity minus infinity or something. Who knows what that is? That's an indeterminate form. Doesn't mean anything. So you got to simplify this. They tell you what to do. I think I'll skip it. I think you guys know what to do here. It says think common denominator. This guy, presumably, you know, this denominator here, it factors, I think, as, you know, x minus 3 times x plus 4, and then get common denominators with these two fractions, put them together into a single fraction, and then plug in 3, and you should get your answer. Okay, so that is that. I will see you guys all on Friday. Oh, and yeah, just to be clear, you know, your homework due Friday, your classwork homework is just homework number 3. Okay, so homework 3 due Friday. See you guys then.